One of the important difficulties in making sustainability decisions is that uncertainty is involved. We can't be sure what the possible outcomes are and what the likelihood is that a particular outcome will come to be. The ideas of randomness and probability are some of the key mathematical concepts that take on uncertainty. We'll examine these ideas for the remainder of Chapter 5. In this video, we'll focus on the basic ideas of randomness and probability, and I'll introduce some tools for describing probability. In everyday conversation, we often use the word random to describe something without a plan, or when we encounter something we find strange. But in mathematics, we describe a process as random if we know what outcomes could happen, but not which particular outcomes will happen. There are many examples in our everyday lives which fit this description. A classic example is a coin flip. There are two possible outcomes, heads or tails, but we cannot predict which of these two outcomes will actually happen. Another event that we treat as random is the weather. For example, we can say that temperature at noon tomorrow will be somewhere between 0 and 100, but we can't predict exactly what the temperature will be. The movement of the stock market is another example, where we know that the markets will close within a certain range, but we can't predict where in that range they will actually land. Although the uncertainty is at the core of randomness, we can still find patterns and trends in random events. Describing these patterns leads to the idea of probability. Just like the idea of randomness, we have informal notions of what probability is. This is sometimes described as personal probability, that is, our personal judgment about how likely something is to occur. This table suggests how many of us may interpret various probabilities. A 0% probability means that an event is certain not to occur, whereas a 100% probability guarantees that it will occur. When we say there's a 10% chance of something occurring, we take this to mean that it's possible but unlikely, and so on. But how do we make this a careful mathematical idea? We can define the probability of an event as a number between 0 and 1 that reports the likelihood of the event's occurrence. There are two ways to determine the likelihood of an event's occurrence. If the outcomes are equally likely, then the probability of any particular outcome is simply 1 divided by the total number of possible outcomes. For example, flipping a coin has two equally likely outcomes, heads or tails, so the probability of each is 1/2, or 50%. Alternatively, we can think of probability as the long-run relative frequency of a particular outcome. That is, if an event is repeated many times, what fraction of the time does a particular outcome occur? We can apply this idea to the weather. Weather predictions are based on weather models, which simulate the possible weather for a given day and place many times. If it's reported that there's a 40% chance of rain, we can interpret this to mean that in 40% of the simulations run, it rained. An important result in probability is the law of large numbers, which states that the relative frequency of a particular outcome settles down to the true probability as the number of trials increases. One consequence of this is that the two methods for determining probability, through equally likely outcomes or through long-run relative frequency, should give us equivalent values for probability. To finish this video, I'll define a few key probability vocabulary terms and then apply them to some examples. A trial is a single instance of a random process. The sample space is a list of all possible outcomes for a random event. And finally, a probability model is the mathematical representation of a random process, defined by the sample space and the probability of each outcome. Let's apply these terms to the coin toss example. Recall that we can think of tossing a coin as a random process. For this process, a trial is a single coin flip. The sample space, that is the possible outcomes, is heads and tails. Then the probability model is given by the table, which shows the outcomes and the probabilities for each. This example includes two different probability models, created by the MIT Joint Program on Science and Policy of Global Change. These models predict the likelihood of various temperature anomalies, that is, how much the average global temperature will increase by the end of the century. For these models, a trial is the temperature anomaly of the Earth at the end of the century. Here, because there is only one Earth, there will only ever be one real-life trial. But we can still use probability to help us understand what the scientific evidence tells us about what may happen. This is similar to the weather example, and that such probabilities are based on the frequency of different outcomes in climate simulations. The first model represents a no policy or business as usual scenario. Here, the sample space is the 6 different temperature ranges that are listed. The second model represents a policy scenario, which assumes that aggressive policies are enacted to limit cumulative emissions of greenhouse gases over the century to the equivalent of 3.4 trillion metric tons of CO2. Note that the sample space is different for this model to better capture the range of likely outcomes. In this model, even with aggressive policies, there is still a very high probability of increases over 2 degrees Celsius. The textbook reading on the material in this video does a much deeper dive into various rules of probability. We won't need those rules going forward, and I don't expect you to work with them in this class.